Hi there and welcome to the Auriga Astronomy videocast. Today we're going to look at the electromagnetic spectrum. Now when you think of light, what do you think of? Probably what your eyes can see. But the light to which our eyes are sensitive is just a tiny sliver of the total amount of light that surrounds us. The electromagnetic spectrum is a term used by scientists to describe the entire range of light that exists, from radio waves at one end to gamma rays at the other. In fact, most of the light in the universe is invisible to us. Now, light is a wave of alternating electric and magnetic fields. The movement of light isn't that much different than waves crossing the ocean or a swimming pool. And like any other wave, light has a few fundamental properties to describe it. One is its frequency, measured in hertz, which counts the number of waves that pass a point in 1 second. And another closely related property is the wavelength, the distance from the peak of one wave to the peak of the next. These two attributes are inversely related. The larger the frequency, the smaller the wavelength, and vice versa. Now, the electromagnetic waves that your eyes detect vibrate between 400 and 790 terahertz, THZ. That's several hundred million times a second. And our brain interprets these wavelengths as light of different colours. Red has the longest wavelength and violet the shortest. When we pass white light through a prism, we can see it's actually composed of many wavelengths of light. And the prism creates a rainbow by redirecting each wavelength at a slightly different angle. But light doesn't stop at red or violet. Just like there are sounds that we can't hear but other animals can, and smells that we can't detect that other animals can, there's also an enormous range of light that our eyes can't detect, and some other animals can. In general, the longer wavelength comes from the coolest end and darkest regions of space, and the shorter wavelengths come from the extremely energetic phenomena. Now, astronomers use the entire wavelengths of the electromagnetic spectrum to observe a variety of different things. Radio waves and microwaves, the longest wavelengths, the lowest energies, are used to look inside dense interstellar clouds and track the motion of cold, dark gas. Radio telescopes have been used to map the structure of the galaxy, while microwave telescopes are sensitive to the glow of the Big Bang. Infrared telescopes excel at finding cool, dim stars slicing through the interstellar dust bands and nebulae, and even measuring the temperatures of planets and other solar systems. The wavelengths of infrared light are long enough to navigate through the clouds that would otherwise block our view, and by using large infrared telescopes, astronomers have been able to peer through the dust lanes of the Milky Way into the core of our galaxy, and the replacement telescope for Hubble, which is called James Webb, due to be launched within the next couple of years, is an infrared telescope. At wavelengths shorter than violet, we find the ultraviolet or UV light. Now, you may be familiar with UV light from its ability to give you a sunburn. Astronomers use it to hunt out the most energetic stars, identify regions of starbirth, and when viewing distant galaxies with ultraviolet telescopes, most of the stars and gases disappear. All the stellar nurseries flare into view. Beyond ultraviolet come the highest energies of the electromagnetic spectrum, X-rays, gamma rays. Our atmosphere blocks this light, which is useful. It protects us. So astronomers rely on telescopes out in space to see X-ray and gamma ray universe. X-rays come from exotic neutron stars, the cores of supergiant stars that have collapsed in on themselves at the moment of a supernova. The vortex of superheated material spiralling around black holes, or the diffuse clouds of gas in galactic clusters that are heated to millions of degrees. Meanwhile, gamma rays, the shortest wavelength of light and deadly to humans, unveil violent supernova explosions, cosmic radioactive decay, and even the destruction of antimatter. Gamma ray bursts, a brief flickering of gamma ray light from distant galaxies when a star explodes and creates a black hole, are among the most energetic singular events in the entire universe. But it's not just astronomers using telescopes that can see these wavelengths of light. Certain animals, cats, see in infrared, which enables them to hunt at night. And kestrels, which we often see hovering over motorways, see ultraviolet. They can actually see the urine trails of mice, which is what they're looking at. Well, the bottom line is the electromagnetic spectrum describes all the wavelengths of light, both seen and unseen. It's not that difficult. So, I hope you enjoyed this episode, and do join me next time. Thank you.